All right, so we're switching gears completely today. We're done with D&M, and we're doing 2 weeks of thermodynamics. So the first part of the lecture is going to be stuff that you've probably heard in some other class. We're defining what is temperature. Then we'll define thermodynamics a little bit. It gets more clearly defined next week. And we talk about types of thermometers. We'll talk about thermal expansion, and the bulk of the lecture is heat capacity, specific heat, calorimetry, and phase change, and then we'll finish up with mechanisms of heat transfer. So, temperature uses capital T when we're describing temperature in an equation. So we know that this is a measure of how hot or cold something is. When temperature changes, it can change the length or volume of objects, the pressure of gases. When we get to 223, we'll talk about how temperature can change the color of objects if they're really hot. It can change the conductivity or resistivity of metals. So temperature has a big influence on materials. The SI units are Kelvin. There's no degree symbol. We don't say degrees Kelvin unless we're making a mistake, which I do sometimes say that, but we're not supposed to say degrees Kelvin. So we will define the Kelvin scale today if you are new to it.
I have a question. Why isn't it degrees Kelvin? What's the definition of that degree?
I don't know the answer to that.
I would have thought of it as just this high. This is the degree of the temperature, which is the number.
I don't know why they don't say degree Kelvin. The book might offer a better explanation, but I don't know. But that's a good question. We define the lowest level of temperature as absolute 0 Kelvin. Nothing can be colder than that as far as we know. And there's no upper limit. As far as we know, there's no, anything could be as hot as, there could be things that are infinitely hot, I guess. So room temperature is about 290 Kelvin, so we're not anywhere close to absolute 0. Thermodynamics is the study of the thermal energies of a system or environment. And thermal equilibrium is defined when multiple bodies are in contact they're in the same environment, and over time they reach the same temperature. I'm saving you guys from a boring lab that studies thermal equilibrium, the process of objects coming to room temperature when they're not at room temperature. So I've decided to scrap the old Lab 4, which was putting thermometers in cups of hot water and watching them cool. Because we all love watching the grass grow and watching paint dry. So why not watch water cool down? No, it's about the most boring lab ever. So we're going to do something completely different, and I'll explain it at the end of class, at the end of the lecture, and hopefully you guys enjoy it, but it's completely new and very poorly thought out. So hopefully it like the car lab is fun and not awful. So okay, the 0th law of thermodynamics. It got this name because they came up with the first 3 laws, and then they realized that there was something more fundamental that was just so obvious. They decided to go back and add a 0th law. They wanted it to be the first one, but there already was a first one. And the 0th law just says basically that objects that are at different temperatures, if they're in contact, will eventually come to the same temperature. And so it's got this like very textbooky definition.
How long did it take you to figure that one out?
Oh, I don't know. It was in a span of a couple decades. The book has got the date, so they knew this, but that's the thing is they didn't think it was necessary to make this a codified law. But then when you're writing your logical proofs, you keep saying, well, we know this to be true. Then someone's like, maybe we should just call this a law. So that's what they did. Okay. So thermometers, they're used to measure temperature, as we know. The most basic thermometer is a bimetal strip. And that's where you take two metals that have different temperature, their expansion coefficients are different as the temperature changes, and you bond them together. So as the temperature changes, one metal is going to expand more rapidly than the other metal, causing the metal to bend. And if you coil them up into a coil like this, then as one bends more than the other, it causes this little needle to turn. So that's the basis of these very standard outdoor thermometers that you have. So all you need is to just calibrate your scale once you've coiled up your bimetal strip. Not the most accurate thermometer in the world, but it does a really good, it's a pretty good job. So that's your most basic thermometer. We all know about alcohol and mercury thermometers. You put a pool of a very expandable liquid in the bottom, and then a very small capillary that liquid can expand into as temperature changes. And then as long as it's calibrated, you put the markings on the scale to tell you what the temperature is at different levels of that liquid. That depends on the scale being very well calibrated, so sometimes they might not be super accurate, but they're pretty good. Now, if you want the most absolute accurate way of measuring temperature, the constant volume gas thermometer is the way to go. So you've got a canister, thick-walled canister. Its volume is not going to change, and it's filled with a very small volume of gas, and it has low density. So for a very small volume of gas, it doesn't even matter if it's the same type of gas, as long as it's a small enough volume, all the gases will have the absolute pressure, or will have absolute pressure, which is zero pressure, at exactly 0 Kelvin. So all gases sort of converge at the same pressure and temperature point, at 0 pressure and 0 Kelvin temperature. So that's what's used to calibrate this thermometer, and then once you've got a calibrated constant volume gas thermometer, this is used to calibrate all other thermometers. So to explain this in a little more detail, if you've got, these are different gases, so that, I don't know what kinds of gases these are, but you could have like nitrogen, helium, oxygen in that tank. And if you plot the pressure, so this is a pressure gauge, as you cool down the volume of gas, it will fall on a linear line, and you can extrapolate that line. And what I was saying is that all gases converge, their lines all converge at the same point, 0 Kelvin and 0 pressure. So all you really need is 2 points to figure out the slope of that line, and so this calculation here is the relationship between the temperature and pressure at 2 different points along that curve. You don't really need to write that down. We're not going to do anything with it, but that's the basis for the Kelvin temperature scale. That's how Kelvin is defined, is using absolute 0 Kelvin, and that's where absolute pressure, 0 pressure would be for every gas. Okay, so talking about the Kelvin scale in more detail, the other critical point besides 0 Kelvin that helped define the scale is called the triple point of water. And the triple point of water is the point where you can have both solid ice, liquid water, and water vapor all coexisting. And it's just 0.01 degrees Celsius above 0. So it's just above the point when water freezes. And the triple point of water is at exactly 273.16 Kelvin. And that at that point, that weird coexistence of solid, liquid, and gas water, you also have the triple point of pressure, which is 610 pascals. Okay. What's that?
What does it mean, triple point of pressures? You have 3 different pressures?
No, just that it's related to the triple point of water. So the triple point pressure is the pressure when you have the triple point of water. Yeah.
So you have to have both, though, right?
Yeah, they all. Yeah. So if you're at the triple point of water, then this is the pressure you'd have to be at.
It's like the phase diagram. They all converges with pressure and temperature at that one little point.
Yeah. Yeah. Okay, and so we're more familiar with Celsius and Fahrenheit scales. The Celsius scale is based on the freezing and boiling point of water, which makes a whole lot of sense. The freezing point is defined as 0 degrees Celsius. The boiling point is defined as 100 degrees Celsius. You have 100 even markings from 0 to 100. So the unit, or the distance between degrees Celsius is the same step size as the Kelvin scale. So the Celsius scale makes a lot of sense for everyday usage because we're in the range of liquid water most of the time. When it's warm, like it is today, there's liquid water outside. So using the Celsius scale makes more sense than the Kelvin scale in everyday usage. Otherwise, every value you had, you'd have, the temperature outside. Instead of saying it's 30 degrees Celsius, you'd have to say it's like 200 or like 300 degrees Kelvin. So it's easier to use the Celsius scale, but it's really easy to convert from Kelvin to Celsius. So you just take your Celsius temperature, you add 273.15, and that's how you get to the Kelvin temperature. All right, now the scale that makes absolutely no sense at all. The one that we use. The Fahrenheit scale. This is based on the freezing point of brine and its boiling point. Brine freezes at 32 degrees Fahrenheit and it boils at 212 degrees Fahrenheit. Very random. So here's our conversion. Oh, and the step size is different, as you could probably guess. So a change of 5 degrees Celsius equals a change of 9 degrees Fahrenheit. So this is your conversions from Fahrenheit to Celsius and from Celsius to Fahrenheit.
What's brine?
Brine is seawater.
Oh. Why didn't they make that 0?
Don't ask me. It's a dumb scale.
A lot of Americans scale.
Fahrenheit's a German name, so,
That's true.
wait, Germany. Yeah. Thought it.
And I mean, I've learned this conversion like 3 times in school or something, and I still never remember it. So, and it's like, I don't know. I mean, even saying that Celsius scale is more logical, I don't think in Celsius because I was born and raised here with this dumb scale. So, these are the countries of the world that use the Fahrenheit scale. This is the country of the world that uses the Fahrenheit scale. Yeah, just us. So this is a nice infographic that shows you the comparison between Kelvin, Celsius, and Fahrenheit. So that's kind of a handy-dandy thing to keep in mind as you're trying to think about what a value in Kelvin actually means in what our brains logically resort to in the Fahrenheit scale.
Was Celsius at one point the main SI temperature?
No,
No?
it's always been Kelvin.
So I just remember at one point being drilled that Celsius was the SI unit, and then like somewhere middle through high school I started being taught Kelvin, because all of a sudden this is the SI unit.
That's because schools lie.
Well, yeah, I know they lie.
They lie about everything.
Yeah. So
Yeah.
I wasn't sure if there was a shift or they were just being stupid.
No, they're being stupid.
Yeah, okay.
Like, don't talk science with, no, I shouldn't say, never mind. I just keep my mouth shut.
All right, directly to the high
Such
school.
thing as square root of -1.
Oh, really?
There it is.
Well, I don't know. The one that always pissed me off, and I get it now that I have a kid, but I was really annoyed when they told me that the Earth was round, and then we found out later that the Earth isn't actually round. It's actually really close to round, so I get it. Trying to explain to a 3-year-old that the Earth isn't exactly round is not a conversation you even want to go down. Trust me. I try and over-explain things to my daughter. It's bad news. All right. Why does heating the lid of a jar under hot water make it easier to open?
Thermodynamics.
Okay. All right. Gold star. More specifically?
The lid expands.
Expansion.
Yeah, thermal expansion. But why doesn't the jar expand too at the same rate that the lid expands?
It's made out
Well,
of
Different materials.
insulator.
Different materials.
Made out of time.
The lid is a lot smaller than the jar, so it takes a lot longer for it to
What are we defining as a jar and what are we
expand.
defining as the lid?
The metal top is the lid and the glass part is the jar. Yeah,
Oh, okay.
Because I mean, there are different
that's true. Okay. I guess if you've got something in your brain, then, okay. Yeah, so, yes, metal expands more rapidly than the glass, and that's what causes the lid to open. Or you can be like me and just smack jar lids against the countertop and break the seal that way. Yeah, Thomas?
If they were both the same material, would the lid still want to come off more easily just because the jar is bigger?
No,
Take longer to heat?
no.
Okay.
If they've come to thermal equilibrium under the hot water, then they're both at the same temperature. They both expanded at the same rate, so that wouldn't be a good idea. But
Even though the geometry is different?
yeah, because the way they design the lid is that it's a perfect fit. So the geometry of the lid is identical for the top of the jar and for the
Yeah.
what is it? Knurling? No.
Just thread.
The threading on the lid.
Usually
Yeah.
they'll make the thread out of plastic when you have a metal jar and a metal lid. The
Oh.
thread is usually made out of plastic.
Oh, there you go.
You take the lid off, you'll see it's like, oh, that's why they do it like that.
Yeah. Okay.
You can see it on the like stainless steel water bottles and stuff like that.
Oh, yeah. Well, yeah, they use the plastic lids. But there's times when you want your two metal parts to expand at the same rate, and that's when you make an airplane. It's very important that the rivets expand at the same rate as the airplane. And in fact, they want that airplane to stay together so much that they will drop the rivets into liquid nitrogen and then put them in the hole and rivet them closed so that when they warm up, they already expanded to fill that gap at room temperature. So when the plane goes up into the upper atmosphere and it's really, really cold, if the rivets contract a little bit, it's still a tight seal. You don't want your airplane shaking apart when it gets cold. That would be bad.
So if we make liquid nitrogen guns and shoot the planes, they'll shatter, right? Because they'll contract.
Well, I think it would do more. There would be other things that happen far sooner than the rivets falling out. Okay, so
another L.
yes, another L.
What does it do?
You're never going to have a problem that has both inductors and thermodynamics in the same problem on this test. So you don't have
On
to.
this test?
Yes, I'm not saying in the world. But on your final, you're not going to have a problem that has inductors and thermodynamics questions. So you don't have to worry about mixing up L's. Don't worry, your lab. The lab we're doing starting today, you'll get to combine the two, but not the homework problems or the test problems. So
the L is
length. Yes, this is length. This is just about linear expansion. So if you have a rod and it changes temperature, the length of the rod changes. Then the amount that it changes is dependent on the material. So we have a coefficient of linear expansion called alpha that's material dependent. So table 17.1 in your book has all of the alpha values. The units of alpha are 1 over degrees Celsius or 1 over Kelvin. So whatever temperature you're in, whether you're using Celsius or Kelvin, then that's the units you want to add to alpha. Since the scale of the Celsius scale is the same as Kelvin, it really doesn't matter. It doesn't change the alpha value whether you switch the units on it. So 1 over degrees Celsius. Okay. All right. So this is a pretty straightforward equation. And if you're talking about volume increasing, you get another very similar looking equation for volume expansion. So these values are the initial length and the initial volume. Oh, did L naught and V naught? Did I miss the L naught on the previous page? Oh, they didn't say L naught. Well, L naught makes more sense, so whatever. So beta is defined as the coefficient of volume expansion, and it's just 3 times alpha. All right, so we've got one problem that we can do to try our skills using this equation. So example 17.3, you've got a 200 cubic centimeter glass flask that's filled to the brim with mercury at 20 degrees Celsius. How much mercury overflows when the temperature of the system is raised to 100 degrees Celsius? And it gives us the coefficient of linear expansion for glass, but it doesn't give us the coefficient for mercury, so I'll give you that. And you guys can work on this in groups for about 5 minutes.
Wait, is that Kelvin to the -1?
Yep, 1 over Kelvin. Kelvin to the -1. All right. So try your hand at this one, and we'll talk about it if people are getting stumped.